Okay, worksheet 2, angular kinematics. Okay, so we have some kind of cylinder here, and some bug is running around this cylinder, and tells us what the radius is, tells us what the average angular speed is, and wants to know what the displacement, angular displacement. Okay, so that's like d equals v bar t. D equals v bar t. So they want to know d, they know the time, and we know the speed. So this is omega bar, and this is the time. And so I can figure out what the angular displacement is, and that's in radians. Okay, what is the arc length? Okay, S equals r theta. So once I know what theta is, I know what r is, so r times theta gives me the arc length. Okay, so that's how you do that problem. This is a similar problem. Somebody's running around this 30-meter diameter dome, and we do it for 120 seconds. They tell us what the average angular speed is, and we want to know what the angular displacement is. So d equals v bar t. We want to know what d is, and that's in radians. I know what the angular speed is, omega bar. I know the time. Solve for d. Okay, that's pretty easy. Number 3. So this wants to know what the average angular speed is. That's omega. Okay. So they're telling us what the arc length is. Okay. So if we take the arc length divided by the time, that would be the velocity. So this really is the arc length s. And we can solve for v, which would be meters per second, because we know the arc length and we know the time, so we can solve for v. And we can use v equals r omega then to figure out the average angular speed. So we'll know what the linear speed is. We know the radius, so we can find the angular speed. Okay, average angular speed has to be in radians per second. This tells us revolutions. So in one revolution, there's 2 pi radians. So we have to take 16 times 2 pi to figure out what the total angular distance is, theta. Time has to be in seconds, so we have to convert that into seconds. And so once we get that, then we can use d equals omega bar t. We'll know what d is. We know the time in seconds, and so we can solve for omega bar. All right. Okay, so this says it has the same angular speed as Earth. Well, for Earth, we travel through on our axis here. So here's the planet Earth. Okay, we spin on our axis through 2 pi radians in 24 hours. So let's figure out the angular speed for Earth. Let's see, theta d equals v bar t. This would be 2 pi omega, and we have to put this in seconds. So it's going to be 24 times 60 minutes in an hour times 60 seconds in a minute. And so now we can solve for omega for the Earth. Well, that's how fast this one is spinning as well. So now we can use the same equation again. We just found omega. D equals v bar t. We know v now. We know what angle it goes through. And so we're trying to figure out what the time is. Okay. Okay, so they're telling the arc length that it goes through will be this distance. Okay. All right, so S equals R theta. So this is going to be the arc length. It has to be in meters though. They give us the radius, which is 2 meters. And so we can solve for theta. We can figure out how many radians it goes around. And then we can use d equals v bar t. They give us the speed. We'll be able to solve this for theta, and then we can figure out the time, how long it will take. Okay. This is an interesting problem. Okay. Okay, so it tells us what the speed of the bullet is going through here, and it tells you in the time it takes for the bullet to go through this plate, and then this plate it traveled through 0.54 radians. And we know what this distance is. So using the speed of the bullet, we can use d equals v bar t. They give us what this distance is 2. And we can find the time it takes for basically this wheel to travel through 0.54 radians. Okay, then we can use d equals v bar t, where we know what d is 0.54. We just found the time, and we can solve for omega. So we're trying to find the average angular speed. By the way, this is one of the ways that we could work this in reverse to actually figure out the speed of the bullet. This is also similar to the way we kind of figured out what the speed of light was in the very beginning, the early experiments to figure out the speed of light because it's so fast. Similar to this is with light, with rotating, you had little cog teeth in it cut out, and so it let the light through or not if it just had the right frequency. And then later on they used mirrors. Okay, so for this one, we know what the angular speed is, and it wants to know how long it will take for it to go around this island exactly 6 times. So we can use theta equals omega bar t again. So we know what the speed is. We actually know this distance as well because it says 6 times. So this would be 6 times 2 pi. And then we can solve for time. Okay. So again, in the previous problem, I talked about the angular speed of Earth. And so we can find that angular speed of the Earth. And then it wants to know what angular displacement. So we could use that speed we found in that previous problem. So we'll know what that is. We know the time. It has to be in seconds though. And so then we could figure out what that angular distance is. That'll be in radians. It says the Earth's rotation is counterclockwise, so that would be positive then. So whatever we get is a positive answer. So for this, if it says that we make one revolution in this amount of time, we can use that information to figure out what our galactic angular speed is. So we know one revolution is 2 pi radians. We know the time, that has to be in seconds, by the way. And so then we can solve for omega. It says the solar system has a lifetime of approximately 4.5 billion years. So we want to figure out, okay, let's find the angular displacement in that amount of time. So we use the same equation again. So we now know what the angular speed is. We have to convert this time into seconds. We know that speed, and so we'll plug that in and figure out how many radians that it moves through. And that's it.